Hi, my name is Vinay, and in this video we will learn how to make basic gates using DSCH and simulate them. Okay, so in these videos you will learn how to design and use DSCH software, and obviously how you can improvise your analysis skills with simulating the design and making them work nicely. Okay, so let's start. So this is the DSCH software I would be using to illustrate. So let's say you want to make a basic NAND gate. Okay, so this is the symbol library. So you can drag, drop, and NMOS transistor, and you can double click on this. You can see the properties. I am working in 0.12 micrometer technology. So if you want to set that, you can go to File, select Foundry, go to DSCH Rules folder, and click on CMOS 012. So on the bottom side, you can see that it will open the CMOS 0.12 micrometer technology rule settings. Okay. So you can double click on this NMOS transistor and ask him to show all properties. By this way, you can visualize the pins like gate, drain, and source. Also, you can see the W/L ratio. The width here is 1 micrometer and the length is 0.12 as we have selected. So you can change if they are different. Now let's say you want to duplicate this transistor, you can just copy and make a duplicate. Similar way, I can just drag, drop, and PMOS. I can double click on this and I can see the W/L properties. Click show all to see all the properties of this. Okay. You can also ask him to show switching delays. Okay. If they are mentioned. Okay. So I can just copy this, click copy and duplicate this. Now as we are doing a NAND gate, so this would PMOS will be in parallel and NMOS would be in series. I just arrange them in that way. Okay. So we will need inputs. So I take a button for one input, another button for the second input. We will need a ground to connect to the source pin of the NMOS. Just zoom and all. And then we will need a VDD supply like this and an LED for the output. There we are. So to make connections, you can click on add line, then join the source pins of the PMOS and connect the VDD to it. You have to join the drain pin also of the PMOS so that they become in parallel. Now connect the drain pin of the first NMOS to the drain pin of the PMOS to make the contact, which will be the output. Also join this with the output LED. Now you can join this one of the input to the one of the PMOS and also to another NMOS. That makes contact with the one of the transistor pair. As for the second input, you connect to the second NMOS and also the second PMOS. Ensure that the lines can cross each other, but if you see a pip over there, okay, so that means the contact is there. So in case there is a pip made because you stopped while crossing, so obviously he will join the two nodes. So make sure that you don't do that. I can just save this file somewhere in my demo folder and call this as a NAND 1 maybe, or maybe, okay, NAND 1 is good. Okay, so let's simulate this. So I just start simulation. As you remember that the red nodes indicate the logic high and the blue nodes indicate the logic low level of the nodes. So I click, as you remember, for the NAND gate, if any of the input is 0, output is high. So I just click one of the input is high. So one of the NMOS turns on and one of the PMOS turns off, which is okay. The output is still high. But if I click both the inputs, the output instead of going going blue, it goes gray. It is not going to logic low. And suddenly I see that the connection between the two NMOS is not made. Okay, so that means the connection is not complete, hence the output is shown gray. Okay, so I right click and join these two nodes and assimilate back again. So no change at the output with the one of the input going high. If the second input goes high, still no change in the output. But if I make both the inputs high, then the both PMOS are off and both NMOS are on, and output reaches to low. So this is how I can simulate a basic NAND gate. Okay, you can see the pattern-based simulation results over here by timing diagram. You can zoom and reach the area and see how the transitions were made with the change in the inputs. Now, as you remember, I mentioned that the DSCH is for pattern-based simulation. So if you want to see a Spice-like simulation results, you have to go to take help of Winspice. I've already installed the Winspice software, and to take help of Winspice, I can go to File, Generate Spice Simulation, do a transient simulation. 50 nanosecond is good. Step size 1 nanosecond is good. I say run Winspice. There you are. Okay. So how beautiful this NAND gate is working, right? So green one is the input, which is in 1. Red one is the input, which is in 2, and the blue one is the output. Now help me in identifying the output. Okay, how do I do this? How? I mean, like, I just zoom in, but still I see the mixture of 3 colors. It becomes difficult for me to observe the spice results. So how I can do that? So either I can plot separate outputs, or I can just go to this NAND file. So this is, you see, the spice file. I ask him to open with Notepad or maybe any Notepad editing software. So yeah, Notepad is good. Let's close the previous files. Yeah. So you just come down, scroll down, just go to the bottom of the spice file. So you see that he makes a plot command of v1 and v2 and vout. So I just ask him to level shift the outputs. Okay, so maybe I can just level shift the output to 3 volts. I just save this file and double click on this NAND one, which is by default set to open with Winspice. I double click on NAND one. So there you see. Now the both inputs are multiplexed, but at least the output is level shifted. So I can easily identify where it goes high and low. Okay. If you want the inputs also to be separated, you can just simply edit the Notepad file back here. I say V in 1, let it be like this, and I add this to 1.2 volts, and this I make it to 2.4. Save it. So if you make any changes in the file, automatically they are level shifted. The Winspice automatically will execute if there is any change in the file. So there you can see that over here, I zoom out to this area. So here both the inputs are 1, logic high. So then the output goes low. So that's a perfect simulation of the NAND gate. Okay. So this is how you can simulate a NAND gate, a CMOS NAND gate, using Winspice and DSCH software. Okay. Now let's take some example folders from the basic gates. So you can just say, click open file. So there are a lot of example in DSCH software. So you can go to basic gates, and there are a lot of gates like, okay, there's a OR2. Okay. So that's an OR gate. Okay. So here, what do you see here? Okay. So that is an NOR gate. Do you see this? Okay. Maybe what I do is I just save a copy of this file into my demo folder and then start editing this. Okay. So that is and how you make an OR gate. So you take a NOR gate followed with an inverter. So that will make a simple 2-input OR gate. Okay. I can just delete this part because I want to do only CMOS part. So the schematics of the CMOS based OR gate is made like this way. So this is the easiest side, which makes it very easy to understand. So on the left hand side, you can see there are two PMOS in series and two NMOS in parallel. Okay, so that makes an NOR gate. And if you take the output of this NOR gate and give it to this inverter, obviously that will make an OR gate. The same schematic can be laid out in this way. So this is more compact, more nicely arranged, and looks better. But that's okay. I will use the left and one side, okay, and delete the right hand side one. So this is how I have, okay. I delete all the rest of the parts. Now I double click on the gates and show him the properties so that we can visualize what properties they hold and how the results will be plotted. I just double click on each transistor and click on show all properties. So as you can see, all NMOS are 1 micrometer in width and all PMOS are in 2 micrometer in width, which is okay so far. I run the simulation, and if you click on one of any input, the output turns high. So that's what you visualize. And if both the inputs are high, so obviously the output is high. So this works very nicely as an OR gate. You can see the timing diagram, they come well, okay. So you see any gray output, so that means the output was undefined or it was oscillating, okay. So now I want a spice simulation, so I can go to file, say generate spice, go to click on update and click run Winspice. There you see that yes, this guy works as an OR gate, but still, as with the previous one, we remember that we cannot distinguish easily the transition of the outputs. So how we can make this visualize better? So you can go to that folder where you have the spice file. So you see the OR2 CMOS is the spice netlist. So you can open it with Notepad. Okay. Browse to the bottom side of the file and just simply click write plot by 1.2 and add a 2.5 volt, something like this. Yeah. And now double click on this or just open it with Winspice. So let's say if you are not able to find this, so you can just simply write C, write the command microwin, okay, microwin demo slash or to cmos.cir. I think this was the file name, yeah. So if we just type the file name, it will execute the command. Only remember that the file name should not have any spaces in between, because Winspice requires without space file name. So here you can see that if any of the input is high, the output is high. Okay, the blue one. If both the inputs are low, then only the output is low. So this works very nicely as the OR gate. So let's take another example. So I just see the schematic. What if I make an XOR gate? Yeah, from the library I see an XOR gate. Yeah, okay. So I just drag drop this and connect the inputs. Drag drop the LED and join the XOR gate connection with the input and outputs. Yeah, this is ready. So I just simulate this. So I click 1 0. Yes, the output is 1. 0 1, the output is 1. For 1 1, the output is 0. It works as an XOR gate. Nice. I see the timing diagram. Yeah, it works well. Very good. It works as an XOR gate. But what is inside? I double click on this. No, there is no. It's in Verilog primitive. So this is how the DSCH works. It takes Verilog primitive of the XOR gate and simulate this. What if I save this file to the folder of my demo and ask him to generate the spice file and say run Winspice? So he says some errors are there, that node 3 has only one component connected So if I look at the spice file, he has made the input sources, but there are no passive devices, no active devices. Why is that? Because the DSCH is working on a primitive component, and the Winspice or the Spice netlist, they only work on active and passive components. Passive components like RLC and active components like transistors. Now, since this is a gate and it's a primitive component, so there is no description thrown or the spice file is not created by the software. Hence, you cannot do the spice simulation of any gates you make use in DSCH. You have to use only transistors. Okay, so let's say I go back to opening an example in my current DSC's example folder, in the basic folder, and let's say find XOR CMOS. So this is how the XOR gates are made. So this is the 2-input XOR gate connected with the LED. So if you simulate this, so you can see this is the same XOR gate that we simulated. Okay. So then you have another XOR gate. So this is made using only 6 transistors. 1, 2, 3, 4, 5, 6. 6 transistor XOR gate, most of them in different arranged manner. So yes, this is 0, 1. Yep. So this works as an XOR gates. Okay. So let's simulate this, and before that I just copy to my demo folder. So we have a copy of this, and I just keep only one circuit out of all of this. Okay. So I can double click on this, and I just see this MP. You can click on show all properties. I forgot to click on show all properties. Yeah, this is already there. So I just give him the MOS models. This is the MOS model you wish to use. So you can MN012, so that is 0.12 micrometer MOS model. So I just do it that for all of them. I'm giving him the MOS models for the particular technology node file. Yeah, that's correct. Just ensuring everyone has changed. Yeah, this one is left. So you can see all the PMOS are of 2 micrometer in width and 1.12 micrometer in length, which is okay. Okay. So this guy works by inverting the A input. Okay. So if you can see, so what it does when one of the input is high, let's say which is the B. For start, you can see that A, if it is 0, so this node is high. Okay. And this PMOS is connected with the B. So the B is also 0. So that means this PMOS is on and it is connected logic high to this inverter, making the output to low. But if if let's say input A goes high, so obviously this node goes 0 and this guy gets inverted and the output becomes high. So that's a perfect XOR gate scenario. Okay. And if it goes 0, the output goes back to 0. So that's perfect. Follows the input. Okay. So it's a kind of multiplexer, right? Now, if the B is high, then what? When the B is high, okay, so this NMOS gets on. Okay. This NMOS gets on and this PMOS gets off, and this guy connects this inverter directly to the A. So it is just inverting the A input and the output goes high. So it's a kind of multiplexer. Okay, it passing the second input. Okay, so the first input goes inverted and the same input goes straight with the B as a working as a select line. So that's how this guy has designed the XOR gate, the designer. Okay, so you can just check like this. Okay, and then see the timing diagrams. So they come well as per the schematic logic simulation should have been. Now let's see the spice simulation. So you can go to file, generate spice file. Okay, run Winspice. Okay, so there is some conversion has happened, and there is a conversion error because probably there is a loop in the schematic simulation. Okay, in this case, this guy's spice simulation is not able to converge this. Okay, so we keep it to the schematic only. Okay, so this is how you can design various basic gates in DSCH, and there are numerous examples with the help of which you can simulate. I think we can take one more example like complex gates. Yeah. So you can make complex gates also in DSCH. For example, there is an equation which is like this: A ANDed with B or with C. Okay. So this is the schematic required for this equation. So one of the way is that you can make in the series or the hierarchy of the gates. Now that is considered as a poor design because it will add a lot of delays to the different stages. But if the same you can construct with a single stage design, in that case the delays would be less and the results would be appearing faster. So in micro:wind DSCH software, so there is an various complex gate are available like 5 input complex gate or 3 input complex gate. In this gate you can specify your equation like this is A or with B and C, and it will throw you the output as per the complex gate equation mentioned. Okay, so I just delete this part and select this. So here you can see, yeah, so A ANDed with B or with C. So if any one should be 1, then only the output is 1. So you can see there are arrows connected. So these are the arrow markers. So they either connect to this or these arrows. Okay, so technically they are all shortened. Okay, and we see this timing diagrams and go to the results. Yeah, so here you can see that as the B goes high, the ABC2 comes earlier than ABC1. So that guy is faster. So you can see here more zoomed in. So ABC2 comes earlier than ABC1. So you remember the ABC1 is the hierarchical gate structure, whereas ABC2 is from the complex gate inheritance. So there are 4 stage delays, and here there are only 2 stage delays. So that is a good way of designing and basic, or you can say a complex gate with multiple inputs. So this is how in DSCH you can make basic gates and work around with your understanding. Thank you so much.